All right, I'm back. Let's continue with the motion of satellites, the motion of the moon around the Earth, the motion of the planets around the sun. Now, Isaac Newton wanted to calculate the motion of, how fast and in which way a satellite is going to be going as it works its way around an orbit. This is a very difficult problem. It's solvable, and Isaac Newton did it, but it was hard. He didn't have something that we have. He didn't understand the concept of energy, and we have that. And the law of conservation of energy provides us with a tremendous shortcut. It makes this sort of work much, much easier. So let's take that approach. So let's start by thinking about gravitational potential energy. You're already familiar with the formula mgh. In our textbook, the way it's written is U equals mgh. So that's the potential energy of an object of mass m at a height h, above some reference height, for example, above sea level, and then g is the 9.8 newtons per kilogram. However, this potential energy formula won't work for satellite motion because g changes as you go away from the Earth. It becomes less and less as 1 over r squared. So what we need now is a new formula, and this is it. So our book would not use PE, our book would use the letter U right here. So U equals minus G m1 m2 over r. Now, remember I said that the formula, the universal force formula, sometimes is written this way: G m1 m2 over r squared. Well, so here's m1 and m2. Now, this formula could have been written like this: little m, big M, and so like this could have been the mass of the Earth, and this could be the mass of the moon. But anyway, here it's m1, m2. So let's take a look at what this potential let's make a graph. Let's see what a graph of this looks like. Now, you see 1 over r. If you graph 1 over r, you're going to get a hyperbola. And so here's the same formula right here. When you graph this, you don't graph r becoming negative, right? There's no such thing as a negative radial distance. So yeah, this is a hyperbola, but you don't have the other half of the hyperbola over here. That part's gone. So it's half of a hyperbola. Now, look at this. The satellite is actually, let's say it's the moon, it's orbiting like this. So it has a tangential velocity. This is like a three-dimensional representation. It's moving away from us, and then when it's far, it's like over here, and then here it's moving towards us, and then here it's moving this way. So the satellite is going like this. Now, keep in mind that the slope of the right here the slope of this graph is high. Here the slope is less. Here the slope is less. And remember that the negative of the slope is the force. So you can see that because the slope is big, that's telling us that the gravitational force is big right here. You've got a big gravitational force. And then here the gravitational force is less. And here, the gravitational force is quite weak. And this hyperbola, as it goes out to infinity, eventually the gravitational force will approach zero, although it never gets quite to zero. Now, this curve here stops at this place because let's say this was the Earth. When you get to this place right here, you're now at the surface of the Earth, and now once you start going underground, then now you're just considering the mass. Let's say you're here underground. Now it's just the mass of the Earth like that. So anyway, we don't care, right? Satellites don't go underground. Yeah. Bottom line, this is the potential energy of a satellite as it orbits around the Earth. Now, okay, maybe I should talk about this negative sign. Astronomers, physicists, and so on want to keep the math simple. And it turns out that if you want the potential energy to be positive, it's a mess. Instead, what the physicists and astronomers do is they call this place here, this is 0 joules or whatever of potential energy. And so what that means is that when the satellite or the moon or whatever is out infinitely far away, that's when the potential energy, which should be U, is 0. And as you get closer and closer to the massive object, let's say it's the Earth, the satellite's potential energy is becoming more and more negative. Because it looks, when you graph it, when you look at it this way, and you're saying, oh, you're going down, 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 your potential energy is going lower, 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 more and more negative. We call this a potential energy well, right? That's what I'm calling it right here, a potential energy well. Now you can imagine what a black hole's potential energy well looks like. That's interesting. Okay, so now this graph here has consequences. You see, there's the law of conservation of energy. So let's suppose that a satellite has a elliptical orbit, right? So that the satellite goes like this, and then it goes down deep into the well, and then it goes back up like this. Because of the law of conservation of energy, the total mechanical energy has to stay the same. So here it had more potential energy, but it's going kind of slowly. And then here the potential energy has gone way down, but to maintain the same total mechanical energy, its kinetic energy must be a lot more. So its velocity vector v is going to be big here, but its kinetic energy, its velocity is going to be small out there. So that's what this next thing is talking about over here. So so here's the Earth, and we have a satellite that is in a highly elliptical orbit. I should just mention that there are many different orbits for satellites. We have low Earth orbits, which are circular. You have orbits that are quite far away from the Earth, but those are good orbits because they're geosynchronous, which means that like the dish antenna satellites, the communication satellites, they are in these high orbits, and those are good because here's your house, right? Here's your house, and here's your dish antenna. As the Earth rotates, the satellite rotates with it, and so that's what these high Earth orbits are good for. And then you have these highly elliptical orbits. Many satellites are in those. So in a highly elliptical orbit, when the satellite is far from the Earth, when it's far, so you notice here, it's called apogee. G means Earth. Apo means away from the Earth, right? So away, that's how I remember it. Apogee is away from the Earth. And down here, close to the Earth, that's G means Earth again, and then perigee. I don't know how to remember that, but I can still remember it because I know apogee is away and perigee is close to the Earth. So at apogee, the potential energy is big. You see big letters, big potential energy. And consequently, the kinetic energy is small, little letters. When you are close to the Earth, the potential energy is down, it's low. And to compensate, the kinetic energy is big, so big letters for the kinetic energy. Yeah. Now, Kepler, who knew nothing about, to be honest, I don't think Kepler knew any physics. He was a mathematician and a geometry kind of guy. But he figured this out. He didn't figure out the energy part of it, but he figured out that satellites, planets, and so on, when they're far from the thing that they're orbiting, they're going slowly. When they're close to the thing that they're orbiting, they go faster. And that is called Kepler's Second Law. So here it's drawn for a planet. Helios means sun. So when the planet is at aphelion, in other words, away, A for away, from the sun, the planet's velocity vector is small. But when the planet is close to the sun, at perihelion, the planet's velocity is big. Now, Kepler, being a geometry kind of person, expresses this law in a very peculiar way. And basically, let's say you're timing. You've got a stopwatch, and you say, okay, the planet, I'm going to start the stopwatch here, and it's going to go for 1 week. In 1 week, it goes here. I stop the stopwatch 1 week later. And then I do the same experiment. When the planet comes around, I start my stopwatch, and 1 week later, it's here. So, yeah, I mean, it's going faster, so it's gone further. And the interesting thing is that when you do this area, when you work out this area, they're equal. This area equals that area. And if you think about it, that sort of says, yeah, it's got to be going slow here and going fast here. But it's a very strange way of kind of expressing it, but that was Kepler's way of doing it, and that's called Kepler's Second Law, and it's called the equal areas in equal times law. Yeah. Now, this law is really universal. When you have anything orbiting something else, this law works. So it applies to satellites going around the Earth, planets going around the sun, NASA space probes orbiting around Jupiter, and so on. And closely related to that is Kepler's Third Law. Now, Kepler's Third Law doesn't have to do really with the ellipses part of it. Rather, what Kepler's Third Law says is, let's say, I'll go with red. I've got the sun. Here's the sun. And here is the orbit of Mercury. Mercury is close to the sun. And let's see, I'll use blue. Here is the orbit of the Earth. The Earth is quite a bit further away. And then here is the orbit of Mars. Okay, so let's say we compare Mercury and the Earth. So I'm going to call this radial distance here. So we're talking here, yes, these things are going in ellipses, but they're close to being circles. And this r here is the average distance from the sun. So this r, this let's say would be r1. And then let's say we're doing comparing to the Earth, calling this r2. And so Kepler's third law says that the ratio of these radii equals the ratio of the period of orbit. Now, the period of orbit is the time it takes to go all the way around. The way I've got this right now, planet 2 is the Earth. So this would be 1 year. So this would be 1 year squared. And I know that the orbit of Mercury is a lot shorter than a year. It's maybe a month or something like that. So this would be like, let's say it's a month. It'd be 1/12 of a year squared. Now if you carry this out and you cube this ratio, they're equal to each other. Bottom line, what this means is that when the radial distance of the orbit is small, the period is small. Period small means it's going more quickly around the sun. So bottom line, planets that are near the sun are orbiting much more quickly than planets that are far away from the sun. And that is Kepler's third law. Now, I'm not going to do this, but you can actually check. Here's some data for Mercury and for Venus, and you put this into this ratio here, and lo and behold, Kepler's third law actually works. Yay!